This will be part 4 of section 4.4. We're going to pick things up on number 6, where we were trying to maximize the area of a rectangle inscribed inside of a parabola. We've already set up our area equation in terms of the x value, and so now it's just a matter of doing the derivative. So we're going to take the derivative, and that'll give us negative 6x squared plus 24. We want to set it equal to 0. Subtract 24, divide by negative 6, leaving me with x squared equals, that's going to be what, 4? And so I get x equals positive or negative 2. We don't want to use the negative 2 because our x is got to be bigger than 0 and less than whatever this point is right here, which would be the square root of 12. Because that's anything bigger than the square root of 12. Square root of 12 squared is 12. 12 minus 12 is 0. So that is our domain of this problem. So it looks like I'm going to make my sign chart now. I'll put my endpoint. X can be as small as 0, theoretically, and it can be as large as the square root of 12, and 2 is somewhere in between. So I'll plug in a number like 1 into my derivative, and I get a positive 1 cubed negative 24 is a lot bigger. And then I plug in a number like 3. 3 cubed is 27. Now I get, let's see, 3 cubed is 27. That's going to be negative 54. And looks like another positive. And that makes me think we have a problem. So let's see if we can track down any issues. 2x times x squared is 2x cubed. It was negative, so we're negative. 2x times 12 is 24x. Oh, I did not plug it into the derivative is the problem. I plugged it into the original equation. So let's try this again. The derivative is here. So let's do this again. Plug in 1, and I get 1 squared, negative 6 and 24 is positive. I plug in 3, and now I get 3 squared is 9. I get negative is going to be bigger, so it's going to be negative. All right, that makes more sense. So 0 is a local minimum, which is kind of obvious because we already knew that if x is 0, the area would be 0. We increase to 2, and then we decrease to the square root of 12, which would, again, now x would be all the way out here, and the height would be 0. So we would again have an area of 0. Clearly, our answer is x equals 2. And the question says, what is the largest area the rectangle can have? What are its dimensions? So when x equals 2, the length of the parabola would be 2 and 2, so the length would be 4. The height would be, plug 2 into the equation. 2 squared is 4, 12 minus 4 is 8. So it looks like the dimensions are here, and when x equals 2, or when length is 4, height is 8, all the same thing, we should, of course, get an area of 32 units. What's my units? That's number 6. I see no mention of units, so we'll just call it units squared. Let's confirm that just for fun. Let's plug in 2 to the area equation we have up here, and I get, yeah, it's going to work. 2 cubed is going to be 8. I get negative 16 plus 54, which turns out, or 48, which becomes 32. Okay, let's move on to another problem. Let's try number 7. 7 should be pretty straightforward because I've already set it up to be the volume equation, which is a cubic function. And so now when I take the derivative, I get 12x squared minus 92x plus 120. And now I just want to set v prime equal to 0. Let's think about the domain of this problem. We haven't talked about that yet. So the domain, x can theoretically be as small as 0, although that wouldn't lead to much of a box, and as big as 4. If x is bigger than 4, then that would consume more than I have available for this side. So 0 to 4 is going to be my domain. So now when I set this equal to 0, let's have 0 equals 12x squared minus 92x plus 120. And at this point, I think probably the quadratic formula would be our best bet. I'm probably going to get a positive and a negative out of this math, and the negative one I can throw away, and the positive will likely be my answer. That was strange. All right. So I don't think it's really worth our time for me to go through the quadratic formula, but once you get your value, don't forget we're going to do a sign chart, and our sign chart is going to start at 0 and end at 4, and then we're going to get a value right here from the quadratic formula, and we're going to test. We're hoping to maximize the volume of the box, so my guess would be, and we would want to verify it, that I'm going to get a sign chart that is a positive and a negative, telling me that I have a maximum occurring at whatever critical value I find here. So I'm doing some guessing to save some time, but this is a fairly trivial math operation, and you guys should be able to handle that. Looking at number 9, I don't see anything very challenging here. Once again, we're just going to take the derivative. We need to think about domain a little bit. I've only got 800 meter wire, so looks like L is my input, and the way I have L set up, I guess L could be 400, and then it'd have to be 400 coming back, and so that would lead to an area of 0. So 400 is the biggest L could be, 0 is the smallest it could be. Our answer will be somewhere in between. So I think that's trivial enough, you can handle that. Number 10 looks fairly straightforward. We got a little bit of a nasty, well, that's a little bit of an overstatement, I suppose, a little bit of a nasty derivative. Let's at least do that part. So I'm going to take the derivative of the perimeter, and again I'm visualizing this as w to the negative 1. So the derivative, the negative would come down, and then it would become w to the negative 2, plus the derivative of 3w is 3. So my perimeter simply becomes, or the derivative of the perimeter becomes negative 432 over w squared plus 3. And I'm going to go ahead and put it as a fraction. So this guy gets w squared over w squared, leading me to negative 432 plus 3w squared. Now I know that my critical values are going to be whatever the top equals 0, whenever the bottom equals 0 is going to be an undefined, which is also a critical value. That's only going to happen at 0. We haven't talked about the domain of this function yet, but pretty clearly 0 for w would definitely be the lower end of our domain, because w can't be less than 0. And once again we have this issue where we can make w pretty large, and it just forces L to get smaller and smaller. And so without going into it too much, we could kind of, I believe we could kind of say that the domain is going to be from 0 to infinity. Clearly our answer will be nowhere near infinity. So I'm going to let you guys finish this one again. So don't forget your sign chart, and you should be fine. Number 13. It's going to be very similar to the last one. My derivative of this is, I think, pretty easy to find. We're going to have 4, and then again, visualize this as L to the negative 1. So that negative 1 is going to come down. I get negative 400 over L squared. Or as a fraction, multiply by L squared, I get 4L squared minus 400 over L squared. And finding the critical values then is a fairly simple activity. We haven't talked domain on this one, but again, it's pretty obvious L has to be at least greater than or equal to 0. And then, depending on what we let L equal, W will range fairly big. So basically what it comes down to is, again, let's just be conscious of the fact that we have to be between 0 and, I don't want to give it a whole lot of thought here, but the closer L is to 0, if you look back up here at this equation, 50 divided by, actually let's do it this way, move L over, divide by W. The smaller W is, the larger L could be. So again, I believe we're going to go technically to infinity. So find your critical values and sign chart. Okay, so then 15 will be the last one of this video. And this was a strange one in that A and B look like they're variables like all the other variables we've done, but really in this problem, A and B we're going to treat as constants. Theta is the only input. What is the area based on the changing theta? So A and B locked in as A and B. So I'm looking to find the derivative of A, and let's be more specific. I'm looking to find the derivative of A with respect to the change in theta. So how is area changing as theta changes? So this may look like a product rule. It is not. 1/2 AB, this is all just a constant. So when I take the derivative of a constant times a function, we just get the constant times the derivative of the function. And the derivative of sine of theta is cosine of theta. And thinking about our domain, theta could technically be as small as 0 and would lead to an area of 0, or it could be as large as 180. And once again, leading to an area of 0. So, find critical values. We get 0 equals 1/2 AB times cosine of theta. Divide both sides by 1/2 AB, and I'm simply left with 0 equals cosine of theta. And I know that cosine of theta, if we think about the graph of cosine, starts here, and this right here is pi, which is 180 degrees. So the domain of my function of cosine that we're looking is simply from 0 to pi. And between 0 and pi, we have one time when cosine equals 0. So when does cosine of theta equal 0? Only when theta equals 90 degrees. So let's do a sign chart. 0, 180, 90 degrees. Nothing exists out here, nothing out here. Plug in a number to my derivative, less than 90 degrees or less than pi over 2. So I plug in a number like, say, pi over 4. Cosine of pi over 4 is positive, times the constant makes it positive. And plug in something bigger than 90 or pi over 2, and we can clearly see that cosine is negative, and so that makes a negative value. So based on this, it would tell us that we have a local maximum at 90 degrees or at pi over 2. Therefore, answering the question, 15, find the angle, what value of theta will maximize the triangle's area? So my answer happens to be a 90 degree angle. And that should answer it. Okay, so this ends, I think, video number 4, and we'll pick up video 5, probably setting up the remaining problems, and finish off with maybe one more video answering those problems.